Hello friends, I hope you all are doing well. So today we will see how to design one-way slab using a spreadsheet, or we can say Excel sheet. So first of all we will see the problem statement. So there is a slab whose dimension is 3.5 meter by 9 meter, and it is supported by the masonry wall whose thickness is 230 mm, and this slab is subjected to live load of intensity 4 kN per meter square and dead load of intensity 1.5 kN per meter square. The material that we have to use for the design of this slab should be M25 grade of concrete and Fe415 grade of steel. So before going ahead, we need to decide which type of slab is this. Either it is one-way slab or two-way slab, and it might be known to you that the type of slab will be decided by the aspect ratio, that is Ly by Lx. So Ly by Lx, we need to calculate Ly by Lx ratio, that is equal to Ly will always be longer dimension, so 3.5 by 9 meter, the longer dimension will be 9, so Ly will equal to 9 divided by 3.5 meter, Lx shorter span 3.5, that will equal to, so 9 divided by 3.5, so answer is 2.57. 2.57. So aspect ratio that we are getting is 2.57, and it is greater than 2. So obviously, as the aspect ratio is greater than 2, this type of slab is one-way slab, and if this value is less than 2, that will be the two-way slab. So here, as the aspect ratio is greater than 2, that is 2.57, so it's quite obvious that we will decide this slab as one-way slab. So I have a spreadsheet. So first we will decide which type of slab is this. As per the IS 456 page 37, there are three types of slabs. The one-way slab might be cantilever, simply supported, or continuous. So this slab is considered as simply supported slab. So in a spreadsheet there is a 3 option also. Okay, so type of slab, we consider our slab is simply supported slab, so I choose from the drop down option as simply supported, and accordingly the L by D ratio as suggested by the IS 456-2000, if you see the clause 23.2.1 of IS 456-2000 page number 37, so there is given the span to effective depth ratio for the span up to 10 meter. For the cantilever type of one-way slab, it should be 7. For simply supported type of one-way slab, it should be 20, and for continuous type of simply supported slab, it should be 26. So likewise, based on that clause, if I choose the cantilever type, is accordingly change the value 7, and for continuous it should be 26. So by default this spreadsheet will choose the value as 26. Okay, so here our type of slab is simply supported one-way slab, so I choose simply supported, and accordingly the L by D ratio will be 20. I hope you understood. Now shorter span. So size of slab is 3.5 meter by 9 meter as we earlier discussed. So 3.5 meter, longer span is 9 meter. Okay, the grade of concrete that we have to choose is M25 grade of concrete as given in the problem statement. M25 grade of steel, grade of concrete. So either you can directly write here 25, or you can choose from drop down option as 25. Both option is available, you can do whatever you like. And grade of steel, so grade of steel is given as 415, so I choose again you can directly write 415, or you can choose from drop down option as 415. Okay, now the next question is dia of bar. Now it's our choice which diameter of bar we like to provide. So generally in slab we provide the diameter of bar more than 8 mm, so it should be at least 8 mm or greater than 8 mm, but should not be greater than 12 mm. So I choose here as 10 mm diameter of bar. Nominal cover, the cover to the reinforced cover to the slab is generally provided between 15 to 20 mm. So I choose 20 mm cover, clear cover to the slab, and support width is as given 230 mm. So it is 230 mm, it is in mm, sorry, dimension is given here, the support width in mm is 230 mm. Okay, now the next step is load calculation. So first we need to decide the materials. So density of concrete, I hope you know what is the density of concrete. That is density of reinforced concrete is 25, and density of brick. For floor finish we consider the material that we are using, whose density is 20 mm, density is 20 kilonewton per meter cube. And at this stage we need to decide initial size of slab, that is thickness of the slab. At the primary level we need to decide the depth of the slab. Generally the slab depth are taken should not be less than 125 mm. The minimum size of slab that should not be less than 125, or we can say 120 to 125 mm. So remember, the type of slab for the floors should not be less than 120 to 125 mm. So that's why I am choosing from a smaller value, a smaller dimension. If it comes out to be fail, so we will increase the depth of the section. So first I decide the type depth of the slab as 125. Okay, the sheet by default will set the effective depth of the slab based on the cover and diameter of bar chosen. The waterproofing and floor finish. So depth of the waterproofing and floor finish we choose as suppose 100 mm. If I take the 100 mm, so floor finish load will comes out to will be 2 kilonewton per meter square, but in our problem statement it is said that the dead load for the floor finish is 1.5 meter. So accordingly we have to decide the depth of the floor finish. So if I choose the depth of floor finish as 75 mm, see, so floor finish load will be 1.5 meter will be adjusted. Okay, so I have we need to adjust the load here 1.5 kilonewton per meter square by selecting the depth of floor finish as 75 mm. Okay, now lie load is considered to be 4 kilonewton per meter square. Okay, so total load will comes out to be 12.9375 factored value. This is the service value. If we take the sum of all these values, will comes out to be 8.625 kilonewton per meter square, and if we take the factored value, that is 1.5, that is 1.5 multiplied by W. So this is the W 8.625. if we multiply it by 1.5, the value will comes out to be 12.9375 kilonewton per meter. Actually it is taken for the 1 meter width of slab. Okay, that's why the unit will comes out to be kilonewton per meter. So this is the UDL. Now clear span is 3.5 meter, and we need to find the effective span. So how we can find the effective span? So as per the IS code, there's two criteria. As per the IS 456 clause 22.2, if you see, so there is a criteria, the effective span will be least of the following two. That is, first one is clear span plus effective depth of slab. If you take the sum of this value, that is 3.5 plus effective depth of slab is 100. So 3.5 plus 100, that is 0.1, that will comes out to be 3.6. And clear span plus width of the support, that is 230. If we take the sum of these two value, clear span is 3.5 plus width of support, that is 0.23. So answer will equal to, that is 3.73 meter. You check it. Okay, 3.73 meter. So based on these two value, we have to choose the final effective span. So smaller of these two value will be the actual effective span. So minimum of this two value is 3.6 obviously. So final effective span will be 3.6 meter. So I hope you understood how to calculate the effective span of slab. Now finally I have the factored value of load, and we need to calculate the factored moment, positive factored moment in case of simply supported slab. So how we can calculate? So that will be calculated by WL square by 8. That means W total factored load multiplied by effective span and square of that value divided by 8. If you calculate this value, that comes out to be 20.96. Okay, so by default this spreadsheet will calculate the factored moment, and according to this factored moment we need to calculate the depth, effective depth of slab required for the flexure. See, actually there are two criteria to decide the depth of slab. One is first one is serviceability criteria. Service criteria, and second one is flexural criteria. Flexural criteria. But for your kind information, the depth of this slab will be required more for the serviceability criteria. In flexure, in comparison of serviceability criteria, the depth required for the flexure are small, so we concentrate on the depth required for the serviceability criteria. So if you calculate the depth required for the flexure, that is for the movement, will comes out to be 77.94, and we have provided the effective depth as 100 mm. See, effective depth as 100 mm, so it is safe for the flexure. Our requirement is 77.94 to tackle this 20.96 kilonewton meter movement. To cover this movement, we need to provide the depth as 77.94, but actually we have provided the depth as 100 mm, so we are on safer side. So this spreadsheet will by default gives you the indication that the provided depth is safe for the flexure. Here note is also given: in slab, the depth will mostly be governed by the serviceability limit state criteria of deflection. Okay. Now next step is to calculate their reinforcement. So in case of one-way slab, see here, in case of one-way slab, the main reinforcements are provided along the shorter span. I hope it might be known to you. The main reinforcements are provided along the shorter span, and distribution reinforcements are provided along the longer span. Okay, in case of one-way slab. Likewise, we need to calculate the spacing of the reinforcement in the direction of smaller size, that is LX. So first we calculate the minimum reinforcement required. The minimum as per the IS 456/2000, the minimum requirement for the reinforcement requirement for the slab is 0.12% of the cross-sectional area. That is 0.12% of cross-sectional area, that is B into D. That will comes out to be 150 mm square. And area required for the flexure, that is for this movement, we need to calculate how much the steel is required. So the formula is by default is here. So we this spreadsheet will calculate the reinforcement at 651.173 kilonewton mm square required for this movement. Okay, and distribution steel will always be minimum, at least minimum. Okay, this is actually what happened in case of one-way slab. We do need to provide the reinforcement in longer dimension, along the longer dimension, but it is generally provided for the protection against creep and shrinkage. That's why we are providing the reinforcement along the longer dimension, longer sides. So for that we choose the minimum reinforcement, that is 150. Now here we have to decide the diameter of bar along the shorter span. So I choose the diameter of bar as 10 mm, and according spreadsheet will automatically shows the maximum permissible spacing of the reinforcement as 120. We don't go beyond this value. We have to provide the reinforcement spacing below this value. And along the longer side, I choose the diameter of 8 mm. So it shows that the maximum spacing permissible is 335. See, the criteria for the maximum spacing for the shorter span, that is main steel, is 350 mm. We don't go beyond, we don't go to beyond 350 mm in any case. 350 mm. And for the longer span, the maximum permissible spacing is 450 mm. So keep in mind. So here is 120. So I choose the 120. So I choose 120. So it is acceptable. A requirement is 120. We don't go beyond the 120.61. So I am providing the 120. And here for the distribution, the maximum permissible is 335. Okay. So I provide 300. Okay. So distribution reinforcement will be provided at the spacing of 300 mm and main steel is provided at the spacing of 120 mm. Now the last thing that we have to check is the deflection of the slab, whether it is safe or not. So as per the IS 456 2000, we need to calculate the modification factor. So modification factor, first we need to have the area of steel provided, area of steel required. So area of steel required divided by area of steel provided. By using this formula, the spreadsheet will automatically calculate the stress in steel. That will comes out to be 239.47. Now percentage of reinforcement provided. So it is 0.6545% of reinforcement is provided, and by default this will calculate the modification factor as 1.13. Now finally we need to see the span, effective span divided by depth ratio. The actual that is coming in this slab, span to effective depth ratio is 36. However, the permissible value is 22.7. So indication will be revise the depth. It means what? The depth that we have chosen, that is 125 mm, is not safe for this kind of loading. So we need to increase the depth of the slab. As I earlier told you, we will start from the minimum size. So now I am choosing the depth of the slab as 150. So accordingly all the values will be changed. Now we directly concentrate on the spacing. See, for the 10 mm bar, the spacing requirement is 144.21. So what should I do? I will provide the spacing as 120. Okay. If I provide the 125. Okay. So if I provide the 150, the spacing required is 144. So what we need to do? We increase the spacing as I provide 140 mm. For the main reinforcement, for the distribution reinforcement, that is 279 is maximum permissible. So we provide less than this value as 250. Okay. Now again see, it is coming closer to permissible value, that is permissible is 26 and our value is exceeding beyond the 26, that is 29. What? Again we need to revise the depth of the slab. So I choose 180, then directly we concentrate on the spacing. For the 10 mm bar, the spacing required is 160. Okay, 166. So we provide the spacing below of this value, say 1 60, so it is okay. Now longer span, it is required 232, so I provide 230 mm. Okay, now see, the permissible effective span by effective depth ratio is 30 and our actual coming value is 23.581. Okay, so it shows that our slab safe in deflection. So finally we will see the detailing of this slab. So it is like the main reinforcement, as I earlier told you, is provided along the shorter span. So the main reinforcement is 10 mm at a spacing of 100 mm 160 mm center to center. See, 160 mm center to center, as we have chosen here, 160 mm 10 mm bar at a spacing of 160 mm center to center. So it shows by default as main steel 10 mm at 160 mm center to center. Now for the distribution reinforcement, we have chosen 8 mm diameter of bar at a spacing of 230 mm. See, 8 mm diameter of bar at a spacing of 230 mm. This is a distribution reinforcement. If you take this section of this slab, so it comes out like this. Okay, so this is the overall depth of the slab, that is 180 mm. These are the main reinforcements in orange color. The line in orange color showing the main reinforcement, and these circles are showing the distribution reinforcement. Okay, so likewise, and one more thing is the main reinforcement is bent up over the support or near the support. So there is a reason, because the negative moment or tension will be generated near the support. That's why we are providing the crank bars over the support. Crank means what? It is bent up over the support on either sides. Alternate bars are bent up over the support, and it is generally bent at a spacing of 0.1 lx from the face of the support. From the face of support, we are bending the bars at a distance of 0.1 lx, shorter span. Okay, I hope you understand this all explanation. If you like this video, please subscribe this channel, and if you want this Excel sheet, please comment in the description. Please comment in the description, and please contact me. I have given the number in the description. If you face any difficulty, if you have any question, feel free to contact me anytime. Thank you.